Hey, good morning, guys. My name is Dhruva. I am a software engineer at Facebook. And I prepared some of the slides to talk about some of the different storage or database management systems we have. But later on, I found that we actually need to talk a little bit about Hive. So I also added something towards the end. And I would rather take questions as and when I speak. So if you are interested in asking me questions, please ask. But I might not answer it. If it's a long answer, I'll probably defer it towards the end. And I will talk about Hive towards the end so that it falls into the regular panel discussion that we have following our talk. Just a little bit background about myself. I've been at Facebook for a while, mostly working with Hadoop and Hive in the beginning. Had worked with Hadoop at Yahoo before, especially Hadoop file system. And now I've been working on some of our more online or more transactional systems that we have built in-house. That's the structure of the agenda that I have. I will probably skip over some portions very quickly because they're actually in my slides. So if you see my slides later, you will see probably more than what you actually see on the screen now. But I wanted to capture everything so that if you look at the slides later, you will have a good idea about what I'm talking about. Talk about the data model, different types of data, introduce this concept of SLTP, which is kind of different from OLAP and OLTP as far as I'm concerned. Talk about immutable data stores, photos, videos, and analytics data, and then a little bit about why we use Hive. This question, actually, I was talking to Dr. Stonebreaker yesterday, and he asked me this question again, like, why do you continue to use Hive, although the performance is really bad? So I'll try to address a few questions there. This is a picture that is drawn by one of our interns that did summer internship in our company some time back. So what he did was he took a grid, like latitude, longitude of the world, and then he took all the Facebook people, Facebook users, and plotted their hometowns. So this is not actually drawn on a world map. He just took a grid and kind of plotted each Facebook user in the grid. And the funny thing is that shows up the continents very clearly, right? So it's not actually drawn like a world map. You just plot the users on a latitude, longitude basis, and it shows up the world map. So I wanted to bring this up because it brings in data from different databases that we have, different types of databases we have. And also I wanted to mention that this was a project that didn't start with an aim in mind. This is exploratory. So this is what happens when you have big data and you try different algorithms on a big data and some new visual, and you get to understand some new things that you did not realize it was out there. So that's the key point of why we use Hive. So the four main types of databases, that we have, one is the Facebook social graph. So this is a graph database. All users and objects are connected to one another. That's one type of graph. Then the other one is about Facebook messages and time series data. This is like sensory data we collect from many software and hardware pieces. We put it together. It's like a time series data, or you can call it as a database for sensory data. Then we have data stores, photos, videos, and then we have the Hive Analytics Warehouse. So 4 different classes of data. So people have also asked, why don't you put everything together in one box? So I would also like to point out the differences between these 4 types and why we need 4 different systems to handle these. The first one, so on the left side, I have listed all the 4 types of storage or database systems we have. And each column is kind of talks about the size and the resources that it needs to make that system efficient. So for example, if you look at the Facebook graph, where's the plot? Oh, yeah. So if you look at the Facebook graph, this is a graph database. That is in single-size petabytes as far as total amount of data is concerned. And we use MySQL. It's like a sharded MySQL database. And Tau is like a caching layer on top of it. I'll talk a little bit about Tau and the data model, but I'll not go into great detail. So if you have more questions, I can answer them later. And then the bottleneck that it is kind of designed for is to optimize on random read IOPS. So this, I think, is very important for us to understand that why we use different systems. It kind of boils down here. So Facebook messages and time series data. This is sensory data. This is very write heavy. There's a lot of data coming in, very few reads. And then the size of the data is very big compared to our MySQL database. And it's mostly bottlenecked on storage capacity. It's not bottlenecked on like read IOPS or anything like that. So we need bigger and bigger disks and more disks. So that is for time series and Facebook messages. Photos, obviously, it's storage capacity. It's kind of big blobs and kind of more file system-y database there. And for warehouse, we use Hive, HDFS, and Hadoop. And this is like more than 100 petabytes in one cluster. There are many clusters of that size, but the biggest is more than 100 petabytes. And then again, there again, it is bottlenecked on storage capacity. So about query latencies, what are the expectations and what are the design goals for all of these 4 systems? And why we need these 4 different types of systems? So it plays into that area. So for example, query latency on the Facebook graph, we really like it to be in milliseconds and low milliseconds, because a user is sitting at the end of the website on the browser expecting some results to show up in the screen, and we don't want him to be disgusted with the performance of the website. So that's very few milliseconds, and it's quickly consistent across data centers. So what I mean is that not immediately consistent, it's not synchronous, but we try to make sure that the latencies of synchronization between different data centers is immediate. It's obviously consistent within a data center, but even across data centers, we want it to be really, really consistent very quickly. And obviously, no data loss. We can't afford to have any data loss there. For Facebook messages and time series data, we have around, say, 200 milliseconds. Less than 200 milliseconds is acceptable. Question?
I think you're using consistent different than I'm used to. What is quickly consistent?
OK, so what I mean is that consistency across data centers is not synchronous. So if you,
well, I get that.
Right, correct. So how quickly you have to propagate across data centers?
I guessed that, but that's not the normal use.
OK. So consistent within a data center, and again, obviously, we don't want any data loss there. Facebook photos, the latency is around slightly higher than some of our time series databases. That's another reason. And then it doesn't change at all, so immutable database and no data loss. And for Hive warehouse, the query latencies sometimes are less than a minute. That's what it is currently being used for. So if you run a query, even if you're maybe touching 100 gigabytes of data only, you might actually still wait for 1 minute before the results show up. And it's not immediate, it's not consistent across data centers. There are some loose ways that we copy data from one data center to another based on like partitions and very warehouse kind of style. Question?
So do you limit the size of the query in order to ensure it's less than a minute?
No, I'm talking about smallest size queries. Yeah, let's say a query, typical query would be like, say, 100 gigabytes of data. I'm not in this big warehouse. So even if you take 100 gigabytes on one machine, it'll be really fast, right? But if you run it on Hive, it'll probably still take a minute.
So is time series the same as the news feed?
No, time series is like sensory data. So for example, you are collecting metrics from maybe 100,000 objects. These are software objects, hardware objects, applications, and we dump it to do analysis. This is like a metrics, essentially. It's a metrics database. Internal use, yes.
So if you want to do analytics across these 4 systems, what do you guys do?
OK, so I will take that question. Yeah. OK, I'll take this question at the time of the panel. So Facebook graph, this is our this is where the Facebook user data is stored. I believe this is the first or the second time that I'm talking about this, or at least somebody from Facebook is talking about this. So what happens is that our Facebook graph are like nodes and associations between these nodes. So if you look at these, like say this is a user and this is a story. So they're connected by some associations, right? This is basically a directed graph, and it is one-way direction in the sense that you might have this kind of association, but you might not have a symmetric association in the reverse direction. So it's basically a very I should not say simplicity plays a role here. It's very simple in the sense it's a very generic graph model. Now, we don't use a graph database to store this graph model. That's another question that people ask me. But the salient features of this workload is that it is very read heavy. So there's like more than 99% reads on this database, and a huge working set. And most of the time, the reads are for data that is recently created. So there's a lot of creation time locality. It's highly interconnected. There are some analysis that some of our data scientists have done to see if we can partition the graph into, say, 10 disconnected parts or connections with very few numbers, but that's not possible. So it's not easy for us to partition the graph into like 10 different segmented portions. It's constantly changing. And again, like I said, we want it to be consistent across data centers as soon as possible. The two main concepts, talking about simplicity, there are two concepts in this database, objects and associations, right? So objects are like an ID, objects are like an ID, where is that? Yeah, ID with a type of that object and a set of key values associated with it. So for example, if you look at ID this, you can say page and name of the page. You can have multiple key values associated with an object. This is like attributes for that object. Very similar to some of the data, graph database objects or object database that's been out there earlier. And associations are connections between two objects. Like for example, this is an object and this is an object, and this is the type of this association. And these are the attributes associated with that associations. So we have three concepts in this database: objects, associations, and association lists. Association lists are basically all ID2s or nodes that are connected to one ID1 and type. I'm kind of going fast over here, but if somebody has questions later, please ask me later on. This is the model, this is the data model. And the APIs are like object creation, object update, object delete, and object get. So those are the APIs. Those are 4 APIs for objects. And similarly, we have like 5 or 6 APIs for associations. So for example, association create and association delete. There are 2 APIs to do association creation and deletion. And then there are 4 or 3 APIs to read associations: get, range, and count. Most of the time, our application makes a lot of assoc get range counts, which actually translate to like a range query in the data store. So our database is kind of dominated by range queries. So the architecture is kind of a 3-level architecture. That's where all our storage systems are. And this is where we have a caching tier. Data is cached from the storage onto the caching tier, and then the web servers access it here. So this is, again, the architecture is kind of pretty simple and not very complicated. The reason we have these 2 tiers is that we need to scale out the storage based on the size of the data. And then we need to scale out the cache based on the access patterns and the hotness and read frequencies of that data. So that's why they have 2 different layers. This cache is like a write-back cache. So applications, when they update the cache, it automatically gets updated into the database. The data is sharded, and so we never so all our data, all these associations and objects are kind of sharded, in the sense that we create like a bazillion number of shards and spread them along these databases and these caching machines, and we actually never automatically split a shard. So all the shards are kind of kept small in size, say let's say 5 or 10 gig, and there are manual processes to splitting a shard, but we don't use automatic ways to split shards. We move shards around, and when machines fail, we load balance, but we keep shards as it is. Keeps life simple. That is, again, so I'm working on a benchmark which actually simulates this workload. And we'll be publishing that workload very soon, open source, and that workload that will describe how our workload is on this graph database. So messages and time series data. We keep all our messages, chats, emails, SMS, everything in one storage system. This is where we use HBase. The volume is very high, and why we choose HBase again. The reasons especially is because we are bottlenecked by storage capacity. We are not bottlenecked by IOPS or CPU or RAM on these machines. So if you need lots of storage, lot of disks to store your data, this is one solution which works really well. We use HDFS, fault tolerant, scalable, all that good stuff. It's really important that we also have a MapReduce tool set to sanitize data in the back end. And the data is open format, unlike traditional database systems, and that helps us a lot because we can have a lot of asynchronous processes doing other things with the data in a much faster way than going through the database API. I think that's very critical to understand that it increases innovation a lot when there are things you can do very fast, and by going through an interface that's not the DBMS interface. Again, so here I make the case that semi-online databases continue to run even if some of the disks have failed or some of parts of the database is missing. That's very important for us because the size of the data is very big. Light transactions, because this HBase and some of these NoSQL databases, they give transactions only on a particular key. So you can do read modify writes, or you can just do atomic writes on the same key. And storage capacity bound rather than IOPS bound. I'm sure people will have questions on this, but I'll take them maybe later. So what we store in HBase, maybe I'll skip this slide for now. So the scale is very big, like I said. It's still kind of read heavy, but it is not as much read heavy as our MySQL databases. It's like 50-50 read to write ratio. All data is compressed and is growing at a very high rate. So that's why we are kind of disk capacity bottleneck rather than IOPS. The Haystack, the photo store, this is the third type of data storage we use. Again, the number of the percentage of is like high tens of petabytes right now, and like every second, I think we have around 5,000 photo uploads. So that's quite high, which is reflected by this number. This is the Haystack discussion that we can kind of forget maybe for now. So this is how data flows into our Hive. So now the fourth type of data is our Hive and Hadoop data. And this is mostly used for analytics and report generation. So data gets generated on the facebook.com website, and then it flows into like a small HDFS cluster that is located very close to where the data is generated. That takes around maybe like 5 or 10 seconds to get in there. And you can actually query that data in a streaming fashion through some of our streaming APIs. This is not part of Hive, but we have built something called Puma. You'd find information about it on the web. People have talked about Puma earlier. So that takes, the query latencies here are, you could query analytics data within maybe a few seconds or within a minute of when it was created. These are very elementary querying, like filtering and count. Not much of aggregation. Well, aggregation also, but not aggregation across long boundaries of time. And then the data gets copied into a big Hive data warehouse. There, the copying is around 15 minutes, but some of them are less, and some of them are slightly more. So we keep copying data from, so we have plenty of these all over in our front-end data centers, and all of them copy data into one central warehouse. I think this is another interesting point why we use Hive a lot, because we copy data into one warehouse, one single warehouse. I have worked with other warehousing systems earlier where people like set up 12 different warehouses or maybe 20 different warehouses. But I think it's very key for us to keep everything on one data center or one warehouse. That lets us query different sets of data, completely not connected data in different ways. Then we also scrape our MySQL databases periodically and put everything here. So now you realize that this is the data where, this is the place where you go where you need to access any kind of data, because we scrape MySQL data in here too. This is the right place to do warehousing. Then we use Hive in two different ways, one for ad hoc analysis coming from there, and one for another periodic analysis coming from here. So, so again, the growth rate for Hive warehouse is like Facebook users increasing in the last 2, 3, or 4 years, 14 times, but you would see that the amount of size of the data has increased maybe like 100 times more, or maybe a few times more than the size of the user growth. So that's because we have a lot of new products and new ways, and people are generating new data. OK, so now I come to this part where the question is that why we still use Hive. So I wanted to trigger some questions so that we can answer some of these when we actually do the panel discussion. Dr. DeWitt and Sternberg, so Dr. DeWitt was my prof at Wisconsin. So I mean, this is just to kind of trigger this conversation, is that why do we, people have benchmarked some of these systems, right? So we are trying to figure out what are the things to benchmark when these, what are the right things to benchmark?
Both here we can get them.
Yes, absolutely. So I think to me it looks like the Hive warehouse, when we set this up, I still remember it's like maybe 5-node Hive warehouse at Facebook. And then it was like prospecting for gold in the Wild West. I think, because it's kind of, you don't know what you're looking for. If you look at a person who came to the Wild West, he never had a map saying that, hey, you need to go to this river to find gold, or you need to go to that mountain to find gold. You don't know where it is, right? So this is what triggers a lot of innovation in our company, because we put all the data in one place, and there is no structured format. It's up to the query, the guy who is using the data, to figure out what is the format of this data. And there's great advantage in keeping everything in one queryable system. So even if a query is 10 times slow, but if we can put 10 times more data into that warehouse, we'll do that, rather than making the query 10 times faster.
So you said it's easy for people to run queries and
Sure,
analyze the data. But what if I'm an analyst, if I don't know what's the data?
yeah. So if you don't know what the data is, then you can use Hive. Okay, I'm talking about that is another part, the crowdsourcing for data discovery. Right, so this is also very important for us. Like, how do you know this is a warehouse where you have 50,000 tables, right? Which warehouse in the world has 50,000 tables? At least the ones I have seen doesn't have, but maybe there are. But that's another question, is that how do you, so we have built tools inside Hive and outside of Hive to be able to do data discovery. For example, when there's a question from a person about some data, it gets redirected to the people who have used those tables earlier. So I can talk about more of these as part of the discussion. And then open data format, I think, is very important for us. We don't want to negotiate, like compared to what he said later. You can negotiate with Oracle. I think we have a lot of people who can write and design new stuff rather than negotiate. So we'd rather write and design stuff rather than negotiate every time you need a new feature. Negotiation is something I'm not very good at. But I'm good in designing new systems and putting them all together. And then shortcomings of the existing DBS benchmarks, I think we need to measure fault tolerance. This is one reason why you use HDFS. I'd like to see an industry benchmark which actually run queries when, like, say, 10% of the disks are being killed at the same time. And it doesn't measure elasticity. So we want to add new machines and remove machines when the database is online all the time, because we are constrained by storage capacity. Throughput, I think some of the benchmarks actually measures throughput. So that's kind of not very important for us. So that's all I have for now, but we'll continue this conversation when we have the panel discussion. Thank you.